So hello students, in the last class we have discussed about the specific heat, and so moving forward we will be going to relate the specific heat with the molar specific heat. So specific heat, as we discussed, is this, that we have discussed about the range of a specific heat, that is from 0 to infinity, and that is corresponding to the case of adiabatic process, and that is corresponds to the case of isothermal process. So specific heat can take any value from 0 to infinity. So then, and we have discussed Cp, Cv. I gave you one example that how these are related and how we can feel that what is happening in the process and what is the specific heat that is required to raise the temperature by 1 degree centigrade in case of constant pressure, that we call as Cp, in case of constant volume we call as Cv, and that are the isobaric and isochoric process respectively. So now what we will be going to discuss is the concept of molar specific heat. So in case of molar specific heat, what happens is, so we know the units of this specific heat that we have discussed as joule per gram per degree centigrade. Now in case of molar specific heat, so it is defined as the amount of heat required to raise the temperature of 1 mole of gas by 1 degree centigrade. So now the unit of molar specific heat is joule per mole per degree centigrade, and in this molar specific heat the symbols we will be going to use is capital C. So that is capital C, that is molar specific heat, and in case of Cp and Cv, so Cp, so it is Cp and Cv, that is molar specific heat in case of constant pressure and in case of constant volume. So how can we relate these two, the specific heat and the molar specific heat? What is the way? So before I am giving you one question. So let's say if the specific heat of hydrogen is of 1 gram of hydrogen is C, let's say Cp, then so that is at constant pressure, then what is the molar specific heat of the gas? Okay, so that's the question. So the answer to this is, can we relate it like this? So 1 gram of, so the specific heat of 1 gram of hydrogen is small Cp, and what should be the specific heat of 1 mole of hydrogen? So we need to calculate the specific heat of 1 mole of hydrogen. So 1 mole of hydrogen has a specific heat, capital Cp. Let's say I can take this at Cv, sort of we are constraining a volume, so we can take this as Cv. It doesn't matter, but still, so that is Cv. So this is small, this is capital. So 1 mole of hydrogen is having this. So in 1 mole of hydrogen, what is the molar mass of hydrogen? That is 2 gram. So 1 mole has 2 gram of hydrogen. So 2 gram of hydrogen means 2 gram of, this statement implies that 2 gram of hydrogen has a specific heat, capital Cv. So from this, 1 gram of hydrogen has a specific heat, that is Cv by 2. So now we can equate these two. Can we equate these two? So yeah, we can equate these two, and so we are from this we will be going to get the relation between the capital C and small c. So Cv is equals to Cv by 2. So that is for the case of hydrogen. So if we want to know the general relation, so what we do is, so in generalize, let's say if 1 gram of any gas, some random gas whose molecular mass is m, let's say 1 gram of any gas, let's say X gas, is small Cv, and 1 mole of X gas has a specific heat, capital Cv, then, and let's say the molar mass of X gas is m. So in case of 1 mole, so it has 1 mole of X gas has m gram. So m gram of X gas has specific heat Cv. So 1 gram of X gas has a specific heat Cv by m, and so we can relate this with this. So what we get is Cv is equals to Cv by m. So similarly, this is true for all kind of a specific heat, so doesn't depend on the process. So we come up with the relation, that is m into Cv, or is equals to m into Cp, or in general if m into C. So that is small c and that are capital C. So these are the some important thing that you need to know. Some questions may come in JE, so you need to understand that fact. So this is all our small c. Maybe because of the writing you may not be able to understand, but still these are small c's and these are capital C's. Okay, so we know this. So now let's solve one question. So question is, what is the molar specific heat of nitrogen if the specific heat of nitrogen is 100 joule per gram degree centigrade. So we know the molar mass of molar mass of nitrogen is 28. So capital C should be small m into small c. So that is C is equals to 28. So this is nothing but gram into 100 joule. So that is gram, degree centigrade, and this comes in terms of this. So this will make it mole. So that is 2800 joule per mole degree centigrade. So that is all. So this is all related about the specific heat, molar specific heat. Now we are arriving some other important concept, that is what we called as Mayer's formula, which is called as Cp minus Cv equals to R. So for now I request you to just learn this, because once we understand the first law of thermodynamics, I will I will tell how this formula is coming, I will derive it. So that is the Mayer's formula. Now the question, another question that we will be going to discuss is that how internal, so I make a comment that heat is internal energy of the system, is some sort of internal energy of the system. So now we need to understand that how that is related to the internal energy. So how this specific heat is related to the internal energy. So we will be going to discuss this. Is related to specific heat, and you just need to learn this formula. So that is internal, so Cv is nothing but du for 1 mole, that is for molar, because Cv we are discussing about molars. This is capital Cv. So this is capital Cv divided by dt at constant volume. So in the some previous classes we have discussed that how internal energy is related to the degree of freedom. So we know that U is nothing but F by 2 RT. Okay. So U is F by 2 RT, and so Cv is F by 2 R. And from the Mayer's formula we can get Cp also. So Cp minus Cv equals to R, and Cp is nothing but R plus Cv, and that is F by 2 plus 1 R. So I discussed it in a brief detail that why we are calling this specific heat at constant volume as internal energy, because we are looking at when we discussed about the notion of internal energy, we discussed it that there shouldn't be any motion in a body itself. So there is no dynamics of the body. Whatever the energy is there is internal to the system. So that's why when we are at constant volume, there is no movement, so there shouldn't be any change in volume, and due to this we are calling that as the specific heat required to raise the temperature by 1 degree centigrade, and that is related to as internal energy, like this. Okay. So this is all about the Mayer's formula and internal energy that is related to specific heat. Now, what F is? F we have already discussed, that is degree of freedom. So, degree of freedom is so for the case of monoatomic gases, degree of freedom is because of the three kinds of molecular kinetic energy present in the three direction. For the case of diatomic, it is 5, so that is F, degree of freedom, and in case of polyatomic gases, that is 6. And for this case we are able to find how specific heat is related to the internal energy and what is the value of Cp and Cp and Cv in terms of degree of freedom. So, what we get is Cp is F by 2 plus 1 into R and Cv is F by 2 R. So, that is this. So, let us make one table. So, here we have degree of freedoms. So, we have Cv, we have Cp and we have gamma, that is defined as Cp by Cv. So, for the case of monoatomic gases, so that is degree of freedom is 2. So, Cv is degree of freedom is 3. So, Cv is 3 by 2 R and Cp is 5 by 2 R, and so gamma is 5 by 3. For the case of diatomic gases, the degree of freedom is 5, so that is 5 by 2 R and that is 7 by 2 R, and so gamma is 7 by 5. For the case of polyatomic gases, it is 6, so that is 3 R and this is 4 R, so it becomes 4 by 3. So, if you see in all of these cases, so this comes out to be 1.76 around, this becomes 1.4 and this is around 1.33. So, if you see that gamma is decreasing, so I am not just keep this into your mind because some MCQ may come in case of JE that how the gamma is rated for the different kind of gases. The physical reasoning why this is happening I will be going to discuss in the later lectures, but for now it is just to keep you remind that gamma for the case of monoatomic gases is greater than for the case of diatomic gases, and the case of I will be going to discuss what is the physical significance of gamma. For now just you keep run. Gamma is just the isentropic constant. Okay. Now, let us discuss one numerical quickly. So, that is, so we have a cylinder, so that is previous year JEE questions, a cylinder with a fixed capacity of 67.2 liter containing helium at standard temperature pressure. The amount of heat needed to raise the temperature of gas by 20 degrees centigrade is, so options are 350 joule, 700 joule, 748 joule and 374 joule. So I request you to pause the video before knowing the answer. So the solution to this is, so at STP what we know is, at STP, when it is about STP, the volume of 1 mole of gas is 22.4 liter. Okay, so delta T is 20 degrees centigrade and we need to find out Q. The gas is given, that is helium. So helium is, we know that helium is monoatomic gas, and so for helium CV, because it is happening at fixed capacity, means that is constant volume case. So CV, we need CV, that is F by 2R, and for the case of monoatomic gas it is 3 by 2R. So Q is, so that is N CV delta T, so N, so we need to find out the moles. So moles is 67.2 liter, that is given, divided by what is the standard for 1 mole, so that is 22.4 and this comes out to be 3. So 3 into 3 by 2 R into delta T is nothing but 20. So what we get is 9 T R, so that is 90 into 8.314, so that comes out to be around 7, so it comes to be around 748 joule. So the correct option is this. So with this I end up this lecture, and in the next lecture we will be going to start with work, and then so on we will be going to discuss the first law of thermodynamics. So I hope you will be able to understand what heat is. Thank you.